Hi, this is Math 7, Unit 7, Lesson 1, Relationships of Angles. So we're talking about some geometry things in this unit, which is pretty fun. So here we go. First of all, it says we're visualizing some angles here, and we're going to look at these two and decide which angle is bigger. Now, the key thing when you talked about this in class today is to recognize when we're talking about the angle, we're talking about the distance or that space from one of these rays to the other. This little gap space right there, that's what we're measuring when we're talking about the angle measurement and deciding if it's greater or larger or less than something else. We're not talking about the length of the sides. That's a totally different question there if you're talking about the length of the side there. So if you're looking at these, you might be tempted to say, oh, the B is bigger. Well, it might be a longer line, but in terms of the actual angle, if we took a look here, maybe did some patty paper tracing, right? And we said, well, let's just trace over that angle line there and get ourselves a copy. So if we're talking about just this angle space, like I drew with my arrow there, that space there, and we slide that over and try to put it on top of A, what do we notice? Yeah, they're exactly the same, right? So while B might have longer lengths or longer line segments there, the angle itself is the same. So A and B are actually equal to one another. There's not one that is bigger. So don't get confused or tricked by line lengths. That part is not what we're worrying about when we're talking about angles. We're talking about this space in between the line segments there. That's the angle plates there. Looking at number 2, it says to identify an obtuse angle in that diagram. When you look at that first, what do you notice? You might notice that you have a 50-degree angle here, a 60-degree angle there. You might be thinking to yourself, I don't remember what obtuse even means. Okay, so let's back up a little bit real quick. Maybe if you go back to what you did in elementary school, a couple of things you might have learned about were things called acute angles and obtuse angles, and maybe even talked about something called a right angle. And if you remember about what those were, a right angle was something that was going to be 90 degrees. So something along the lines of a square, right? So if you took a line like this, if you had a right angle, it was going to be 90 degrees. Acute is going to be less than 90 degrees, like we have here and have here. And obtuse is going to be more than 90 degrees. So again, when you look at these degree measurements individually, we see, okay, there's a 50 degree there, there's a 60 degree there, so where is an obtuse angle at? Because these are both less than 90 individually. And so if you look more closely, we could tell that, well, if I went from this line segment all the way over to this line segment, here to here, now I'm combining a 60 and a 50 to have 110 degrees from here to here, and now I am definitely greater than 90 degrees, so I have an obtuse angle. So that obtuse angle we would call, when we look at the line segments here, we would call it D, A, and B to talk about the line segments we're joining together with that angle. So angle DAB is indeed an obtuse angle. Yep, it doesn't have a number there for you to show you that's obtuse, but you can use what you know about acute angles and add those together to show that there is an obtuse angle in that space right there. Okay, so that's kind of the cool thing with the way angles work. So remember your acute, obtuse, and right angles. We'll talk more about those as we go on. In your next activity, it says to trace one copy of every pattern block. Each block contains either one or two angles with different degree measures. Which blocks have only one unique angle, which have two? And so for that, we have our pattern blocks here, and so they want you to trace these. So we take a hexagon here, and if we trace this down, just do this with you here. Gonna make my lines, make my lines, make my lines. Okay, so there's my hexagon. Okay, I also had a trapezoid. There's my trapezoid. We have this nice little equilateral triangle. Again, it's equilateral because it has equal side lengths. Okay. We have our rhombus. You might call this a diamond one if you're in your class. It looks like a diamond. Sure it does. It's called a rhombus. And then we also have this other crazy rhombus. And there we are there. Okay, and oh, one more. Forgot the square. Don't forget the basic square. And then we have this one. Okay, so those were the pattern shapes that you had, right? So those are what we have in your class. And so when we're talking about which one have one unique angle would be things like the square, where there's the same angle in all four spaces there. So that's a one unique angle one. The triangle, here, here, and here, those are all the same. That's one unique angle. The hexagon is the same in all these spaces. It's the same angle. And again, you could use patty paper to prove that, but just looking at it, you can tell these are all the same spaces, right? So those are ones. When you look at the trapezoid, you have an angle here, this angle, which matches that one, and those are greater than 90. If you're thinking about that right triangle again, right? If this is if the square is 90, this is going to be greater than 90. It goes over that space there, doesn't it? Okay. So again, if you were to stack these on top of each other and say, well, does this fit inside that 90 right there? Not really. I have excess space, so it's greater than 90. But over here, this angle is smaller than 90. I have an acute angle over here. So this has two different measurements. This one here, also, the rhombus, has a large angle here and here, and it has an acute angle on these sides. So that has two unique measurements. And the same is true for this rhombus, right? We have a very large obtuse angle here and here, and on these pointy parts we have an acute angle there and there. So this is one that has two as well. All right, so our unique ones are going to be our hexagon, our equilateral triangle, and our square. And our ones with two measurements are going to be our trapezoid and our two little rhombus things. Okay, so that's the idea there, looking at how they have different angles inside of them. All right, but now let's see what we do with that. It says there in the next page, if you trace 3 copies of the hexagon so that one vertex from each hexagon touches the other, they fit together without any gaps or overlaps. So I'm just going to do it here as well with the real thing so you can see it's not a make-believe picture, right? So when I put these 3 things together, I can get the 3 of the angles to come together and meet at that point right there, which is what's happening in that picture. Same idea, right? No gaps, no overlap. It just fits in nicely. Boom, we're set, right? Use this figure to figure out the degree measures of the angle inside the pattern block. Now, one thing you'll notice when you look at what they've given you is what shape did they draw right here? Well, they drew for you a picture of a circle. There's a circle right here that they drew for you. Okay, so we know that if we have a circle, the degree measurement of a circle is going to be, or it's going to have, a circle is going to have 360 degrees inside of it. Just the way the circle works, right? So when we take a look at this picture here, we can see that, well, all 3 of these angles, when you put them all together, are going to have a sum of 360. Okay, so think of it this way. We have 360 degrees inside that circle. If I divide that by the 3 pieces, piece 1, piece 2, piece 3, divide it by 3 pieces, that will tell me how many degrees or what the angle measurement is of one piece. I've already determined they're all the same size, so I can divide by 3. And 360 divided by 3 is going to be 120 degrees. So what do I know? I know that then one angle in a hexagon is actually 120 degrees, right? So this is going to be 120 degrees on that angle measurement right there. Okay, and so that's kind of the idea of what we have here. So I could also think about, well, if I want to know how many of these would it take to get to 360, I could also write it algebraically a different way, right? If I knew this was 120, I could say, well, if I have 120, how many more of them times how many more, question mark there, would it take to make a whole circle? 360. So 120 times what number gets you 360? Well, that's still the 3, right? So I can use 3 of these to form a circle there. We can do that with some of our other shapes as well. So in part 3, it says, figure out the degree measure of all the other angles inside the pattern blocks that you trace in your first question, and be prepared to show your reasoning. All right, so let's start first of all with the square. Okay, I'm going to draw the square here real quick. I'm going to draw a picture of a square, so we know what we're talking about here, square. And I'm going to use my pattern blocks and see if I can get the angles to come together to form a perfect match there. All right, and so what do you see? By doing this, I can put 4 squares together and have the 4 corners touch. And again, just like before, no gaps, no overlaps. I can have them come together in that space. So let me redraw this on my sketch here, right? So this would be like putting together 4 squares like that. Okay, and just like the hexagon, can I draw a nice circle around that? Sure I can. All right, how many degrees are inside of that circle? What do we say? Inside the circle are going to be what? 360 degrees. Okay, so now I'm taking that circle, and how many pieces am I breaking it into? 1, 2, 3, 4. So if we do 360 divided by the 4 pieces that come together to make that circle, that's going to tell me the degree for each angle right there. And 360 divided by 4 is 90. So we know that one angle measurement inside of a square is going to be 90 degrees. All right, let's see if that works for something else. Let's try your triangle. Here's a triangle. 1, 2, let's see, we're not making a circle quite yet. 3, 4, I don't see a circle quite yet. 5, is 5 gonna make a circle? Nope, let's drop some space. Oh, look at that, let's put 6 together. And when we put 6 together, what can we make? It makes it all fit together nicely. It looks like the hexagon now, doesn't it, right? So with a triangle, I can get 6 of these all together, and I can make that circle on the inside. Let's see if I can draw this for you real quick. This is going to be an ugly drawing, so I apologize already. So it's a triangle, 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 triangle. Yeah, it's not too bad. So I have 6 triangles all together, and I can see that I can put a circle right on top of that. And again, the circle is 360 degrees. So if I do 360 and I divide it by the number of pieces that I have, how many do I have? I have 1, 2, 3, 4, 5, 6. That will tell me the degree measurement for each angle making that circle. Well, 360 divided by 6 is going to be 60 degrees. So what that tells me is that with an equilateral triangle, the angle measurement of one of those angles is 60 degrees. Because it's equilateral, I also know that every angle is 60 degrees in that triangle shape. All right, pretty cool. All right, so that's your, we did the hexagon, we did the square, we did the triangle. Now we get to something like the rhombus. Uh-oh, well, this one's a little different, isn't it? If I take the rhombus, can I turn that into a circle? All right, here's 1, here's 2, kind of, right? I sort of can, except that I can make a circle there, but I don't know what that measurement is going to be, right? I can get those 3 pieces to come together to talk about that top angle, and so that top angle, it does make up a three pieces come together. So let's take a look at that first part. Let's do the top angle. So I'm going to draw my picture here. So this top angle, I can put 3 of these together, like we just saw. All right, I'm going to just try to draw that real quick. What would that look like on my picture if I went to that side? It would be like this and like this. Yeah. Okay, so we're going to redraw that real quick. So if I drew one like, boy, that's really not very nice. So something along these lines where I end up with 3 pieces, right? So again, this is 360. My circle here is 360. So 360 divided by 3 pieces is going to be 120 degrees. So this top angle measurement here is 120 degrees. But I know that there are 2 different angle measurements in this shape. So while that makes 120, what about the little triangle? Well, let's see. How many does it take to get to the little angle down here? I got 1, 2, put another little one there, 3. Put another little one there, there's 4. Here's another little one, that's 5, and another little one that is 6. Now notice, I know these don't all go together like, you know, like the cute way, you know, if you wanted to be cute and fancy. But I can make those these 6 small angles all come together to form a circle right here. So it's going to take, in this case, when I look at the little angle, there are 6 pieces there, aren't there? So here we would do 360 divided by 6, and 360 divided by 6 is equal to 60 degrees. So the smaller angle down here is 60 degrees. Well, let's just see real quick. If this is true, if this little angle is 60 degrees, then I should be able to put a equilateral triangle right on top of that, and it should fit perfectly. Let's just see. Yep, look at that. That does work out nicely, doesn't it? So what do we know? We know that this small angle of the trapezoid is 60 degrees, and it matches the equilateral triangle right there. That's handy. That's pretty cool. Now let's take a look at this top one. It says it's 120 for the big one. Well, we knew that our hexagon angle here was 120. So does this angle, the top part of the trapezoid, fit there? Yep, it sure does. It fits right there, so it verifies that it's also 120 degrees. All right, pretty cool. All right, so that's what we have so far. Can we do that with our other pattern blocks too? Sure. So here is our rhombus. Now our rhombus here, we could make the circle thing again, or we could use what we know. All right, so let's look at the rhombus here. So the rhombus is like this, this, and this for the blue one. So blue one. And so when I take a look at the rhombus, do I see it matching up with any other things? If I take the wide angle of the rhombus, notice that I can get it to do what? Land right inside of the hexagon. So what do we know about the large angle of the rhombus? We know that this large angle is going to be 120 degrees. What about the small angle? Well, it's too small to fit the rhombus, to fit the hexagon. Not going to fit there. Let's try what I do know. I know about the equilateral triangle. So when I put that there, what do you notice? Hey, it's the same size. So what degree measurement is the acute part of the blue triangle right here? That's going to be 60 degrees. All right, working out pretty well so far. Okay, so now let's take a look at our last one, which is the light brown one here. This one's a little bit different, right? It's a lot wider, and a lot skinnier on the acute and obtuse angles. I'm going to trace it real quick. Okay, so it's like this, right? We have a really wide obtuse angle here and a much skinnier acute angle right there. So looking at this one, I know it's too wide. If I put my hexagon on top of that, right, it doesn't even fit in there, does it? Not going to work too well. So that's not going to work. What if I took a couple of the equilateral triangles? If I did a 60 and a 60 together, make 120. What does that do? Does that get there at all? Does 120? Is that going to work? Nope, it's still not going to quite work out, is it? So boy, this is getting to be a little tricky, isn't it? So I can't find one that works. Maybe I'll have to combine it with something else. I'm going to use that space there and see what I can put inside of that gap. I know I have 120 there. So I put 120 to fill that space. And then can I fill that space with anything else? Let's see. Put that is too large. Boy, this just isn't working out too nice, is it? So not sure what I want to do, but I do have a lot of these. So let's see what I can do if I can put a couple of them together. So I have a large one. Look at this. If I do an obtuse angle and an obtuse angle, and it looks like I can put an equilateral triangle in there to make that circle space again. That's interesting, isn't it? Now that's a very kind of complicated algebra problem. We want to do that for where we are. So it's maybe a little too much to what we want to do for this lesson. But here's the idea, right? If I was to redraw this, I have this, 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 and this, and this, 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 and this, and the triangle here. I know that with this circle, I've already used 60 degrees, haven't I? Kind of cool. So I've used 60 degrees, and then I have this other amount here, this angle, and there's two of them. So two of these angles, we'll call it x. All of that, when I add it together, should be equal to 360 degrees. That's a true statement. But the x is going to represent this angle and this angle. Could I solve for that? Sure. Let's subtract 60. And we have 2x equals 300. And divide both sides by 2. And what's the angle measurement going to be? 150 degrees. Now that's a little bit more complicated than you need for this lesson, but it's kind of cool to know that you can figure it out that way, right? Notice here, I can also figure out what? This other small angle, because what shape is right there? Do you recognize that shape? Do you recognize that angle right there? What do you see? It's a square, which tells you what? That down here in this space, because I have a 60, this space makes a 90-degree angle here. So I know about the 60. I don't know about that other one. We'll call that y, because I already used x over there. So 60 plus that is going to equal 90 degrees, because we showed that it was a right angle right there. Kind of cool. So if I subtract 60 from both sides, what is that missing angle measurement? It's going to be 30. So you can play with these pattern shapes to figure out unknown angles and see how you solve things. So it's pretty fun. I find it fun. Okay, let's look at the next thing. All right, so we saw that it's possible to fit 3 copies of regular hexagons snuggly around a point. Okay, each interior angle of a regular pentagon measures 108. So they're telling you about pentagon, 5 sides. 1, 2, 3, 4, 5 measures 108. Is it possible to fit copies of regular pentagons snugly around a point? If yes, how many? If no, why not? Okay, so the idea here is, can I do 108 and get a bunch of these to get together to make that full circle? That's the question, like we did up with our other shapes. Can you make the full circle with 108? Here's what you want to think about. How many do you think it might take? What's a guess? You think it would take 2, 3? I don't know. But that's sort of our idea. And you'll see this problem, by the way, on homework tonight, number 3. So pay attention here. If I look to have 108 degrees there, the question is, how many of those times how many times x will it take to get you to 360? Right? That's what we're asking. How many angles can you have to add together to get up to 360? Let's pretend real quick, just do some guessing here. If you did 108 of those and you multiplied it by 3, like we did with the hexagon, what's 108 times 3? 108 times 3 is 324. Okay, so 324 is less than 360, so you're going to have a gap there. That's not going to work. That's going to be a nope, won't work. So I need to get some more angles in there, right? I'm not filling it up. If I do 108 times 4, if I put 4 pentagons together, what do I have? I end up with 432. Well, that's bigger than 360, so that would also be a nope. So what this tells us is that there's no way to get 3 pentagons to join together, or 4 pentagons to join together, to form that closed gap. So we can do it with the hexagon. It works out just fine. It does that. But if I had pentagons, I could not form a close little snug unit and have all the corners come together like that with a pentagon. It's just not going to work. All right, so it's kind of cool. If you ever look like around at tiles and patterns, you won't see a lot of pentagon shapes in those things because it's hard to do designs and mosaics with them because they don't come together nicely. You'll see lots of hexagons and squares and equilateral triangles, but not the pentagons. Kind of cool. All right, so now we're going to use pattern blocks to determine measurements of some different angles. All right, we've already got some angle measurements figured out. Let's see what we can do here. So this first one, A, well, it looks like it's obtuse. From what I can tell, it's bigger than our triangle, right? So that's not gonna work. But it seems to be something more along the lines of the hexagon. So when I slide the hexagon piece in there, what do I see? Hey, it fits perfectly. So what is the measurement of that angle right there? The hexagon, when I look back at my notes, right? It's gonna be 120 degrees because it fits there perfectly. That's part of that hexagon angle. Over here for B, notice that B is the distance from here to here. We're not talking about that space there. We're talking about here to here, okay? So a little different measurement there. This is gonna be a pretty big angle. I'm gonna have to join some things together that I know. I'm gonna start with let's start with a square. That's a nice straight line there. So I'm gonna put a square there. Okay, and we're trying to fill in that space. Let me shade it in for you, okay? So we're trying to fill in this space nicely with our pattern blocks. That's the angle we wanna know about. So we can fill in that space right there with the square. That's cool. And then look at my hexagon. Right there. Oh boy, that's handy. So let me draw a little line real quick right here just so we can see what we're doing. We know that from here to here is how many degrees? 90 degrees. And we know from here to here, this is hexagon, which is 120 degrees. So all together, we put that all together, 120 plus 90, and we end up with 210 degrees is this space right there. So angle B is 210 degrees. Kind of cool. All right, and finally C, taking a look at C, looks like a line there, doesn't it? But it's going to go from here to here, so we're trying to fill in all that space, going from one side to the other. So what do I want to use? I'm going to use a square, because I notice if I put it on the line, and put that on the line, I'm good to go, right? So if I drew my imaginary line here to show what I'm drawing, I have a 90 on this side, and a 90 on this side, and altogether a 90 and a 90 equal 180 degrees. All right, so we can put two squares together to make that work out just fine. If an angle has a measure of 180 degrees, then its sides form a straight line. So 180 forms a straight line. An angle that forms a straight line is called a straight angle. Okay, cool. Find as many different combinations of pattern blocks as you can that make a straight angle. And so like we just did, we made two pattern blocks like this and put two squares together to make that straight angle. So the idea is we say, okay, cool, I can do a pattern block, right? And I draw that line down the middle. And so what are we saying? We're saying that I can take two squares and I can make that 180 degree angle right there with two squares. Perfect. Can I do it with the other shapes? Sure I can. Take a look at this. Here's a triangle, triangle, triangle. What happens when I take all these triangles and I go like this? Do I have a straight line right here? I sure do. So I have a straight angle right there. How is that straight angle formed? It's formed because I have a triangle, equilateral triangle right there, and an equilateral triangle right here, and right here I have 1, 2, 3 equilateral triangles that form together to make that 180 degrees. Okay? Are there other ways of doing this? Sure. Let's take a look at the hexagon. Now, right now you might say, well, that's not a straight angle. That doesn't count. It's by itself it is, but the hexagon block is not that. But what if we slide in this equilateral triangle right there? What do you notice? Look at that. When we put that guy there, when I add the 60 degrees of the triangle to the 120 degrees of the hexagon, 120 and a 60 is 180. So I can use a hexagon and a triangle to also make that right angle. There are lots of other ways you can come up with, and you can play with the pattern blocks to see what you come up with just to have some fun. I'm going to move on, otherwise I could be here all day. Okay, the next activity in the lesson today is an optional one, so it depends on if your teacher had time to get this or not, but you're talking about using a protractor tool, measuring tool. Okay, so it says Tyler and Priya were both measuring angle TUS. Priya thinks the angle measures 40 degrees. Tyler thinks it's 140. So Priya says 40 degrees and Tyler says 140 degrees. Do you agree with either of them? Why or why not? And so the thing with the protractor is you have to take a look at what it is you're measuring. So I like to I go in the order that the letters come in. So here's TUS. So I'm starting at T, and I'm going to U, and then I'm going to S. So this tells me the space that I'm talking about. This middle letter tells you the angle itself. It's angle U, but we call it angle TUS. So we're talking about this space in here between T, U, and S. All of this space right there is what we're talking about. Now, they both measured it, but one got 40 and one got 140. And you can notice here on this protractor, what do you see? Both numbers are there. There's a 40 and a 140. So, which one do you use? All right, to use the protractor, you want to use the one that starts at 0. okay, whatever line you're talking about. That's why I said let's look at the T first. Because I'm talking about this line T, I know I need to start at this space right there and go that way in my measurement, because that's my 0. So when I start by here, I go 0, 10, 20, 30, 40, and so I'm going to use 40 as the best answer. So I would agree with Priya. She has 40. What Tyler did is Tyler took it from this 0 all the way to 140. He's measuring that distance. That's 140 there. But we don't have a line segment to say what that angle is going to be called. We're just talking about this space right there. Okay, so that's what we would say. All right, so in summary today, did a couple fun things. We said that when two lines intersect and form 4 equal angles, we can call each one a right angle. All right, a right angle measures 90 degrees. So a right angle is going to be 90 degrees. Very good. All right, you can think of a right angle as a quarter turn in one direction or another. Great, so 90 degrees, right angle. An angle in which two sides form a straight line is called a straight angle. A straight angle measures 180 degrees. Got that. And we call that a half turn. So we'll get some turns and stuff, I guess, later on. So a half turn is that. If you think about quarters and half, that's because we're talking about what? We're talking about a circle. And so all the angles together can sum up to make 360 degrees, and that's what we have there. So that's kind of where we are. So it's a quarter because why? It's a quarter of a circle, and it's a half because why? It's a half of a circle, and a whole turn is 360. So those are some fun numbers to work with. Let's see how those work out with our homework. So take a moment to work on your homework, press pause, and then we'll come back and see how you did. All right, homework check time. Here are questions about 2 types of angles. Draw a right angle. How do you know it's a right angle? What is its measure in degrees? Okay, so if I want to draw a right angle, I could just guess real quick, or it might be better to use something that I have. Maybe a pattern block could work, all right? Because I know that a pattern block is going to be 90 degrees. Or perhaps I wanted to use a corner of a book or something like that. So there's one that I draw that's 90 degrees. Now, I know it's 90 degrees and it's a right angle because a right angle is 90 degrees. That's what we call those. And I know it works because the corner of a square is 90. And if I take 4 of those together, 90 of those corners times 4 is going to give me 360, like we saw in our lesson today, forming that complete circle. All right, so 1, 2, 3, 4. I can put them all together. And because the corners come together nicely, I could draw that circle space, and I know that it's 90 degrees. Works out great. So that's what I'm going to use, as a square pattern block. If you use the corner of a piece of paper, right? If I use some tracing paper, some patty paper like this, I could draw a right angle with that, right? It's a little tricky, but I could use that there, come down and draw a thing. It's not very pretty, but it does kind of work, right? So that's the idea. Draw a straight angle. How do you know it's a straight angle? What is its measurement? Let's see what we have here. So a straight angle here, I could again use what? I could use 2 of the 90 degree angles. I can put them side by side, draw a nice line like that, and then where that's at, I could draw my little here to say, well, there's cut in half. I know I have a 90, I have a 90, a 90 plus a 90 equals what? 180 degrees for the whole thing. So that becomes a straight angle right there. Number 2, an equilateral triangle's angles each have a measure of 60 degrees. Yes, that is true. So when you take equilateral, they're 60, 60, 60. Lovely. Can you put copies of an equilateral triangle together to form a straight angle? Explain or show your reasoning. And the answer to that is going to be, yeah, you can. And we did it in our homework, or our lesson today. I could take them like this, like this, like this, and I could put them together and make for myself a nice straight angle like so. Again, it's hard to do it sometimes with the blocks, they move, but you get the idea. So I could form them like this. And I could take one out and draw the line that goes there. And take one out and draw the line that goes there. And so sure enough, we can see that I can take 3 equilateral triangles to form that 180 degrees right there. which makes total sense because if it's 60 degrees, 60 times 3 of those is equal to 180, and 180 degrees is a straight angle. Can you put copies of equilateral triangles together to form a right angle? Explain or show your reasoning. Okay, so if you just try to do it with the pattern blocks here, if I put two angles together like this, right? So here's an angle 1. Let's just draw it. All right, so here's angle 1. Whoops, angle 1. And then here's angle 2. Let me draw this one now. Angle 2. Right, we know this is 60 and this is 60. So 60 plus 60 is 120. I want to make a right angle. A right angle is going to be 90 degrees. So this is greater than 90, and that's with 2. 3 is not going to help. It's going to make it too large, isn't it? Okay, so it's not going to work. So 60 times 1 gets you only to 60. That's less than 90. It's not a right angle. 60 times 2 gets you 120. That's greater than 90, so that's also not a right angle. So what do we have then? Well, basically we say, nope, it's not possible. It's not possible to use the equilateral triangles to make a 90-degree angle, a right angle together. Here is a square and some regular octagons. Well, actually they're not right here. They are on my next page. So here's a square and some octagons. Octagons have how many sides? Octagons like an octopus, so it has 8. 1, 2, 3, 4, 5, 6, 7, 8. Awesome. In this pattern, all the angles inside the octagons have the same measures. Cool. So these are all the same measurements. Right there, right there, right there, right there, right there, right there, right there. The shape in the center is a square. Thank you very much. Find the measure of one of the angles inside one of the octagons. Okay. So to do that then, what we're talking about is this. We're saying, well, let's pretend that we draw a circle right around one of those spaces where they come together. So there's my circle space right there. You with me? My circle space. Do I know the degree of this part of the circle right there? Yep, I do. That's a square. That's 90 degrees already. Perfect. Now I have these two pieces. We can call them X and we can call it X. Why are they both X? Because they told us that the octagon measures, angle measures are all the same. So 90 plus an X and another X, so two X's, all those things together, 90 plus X is going to all add up to what big degree? How much is in a circle? 360 degrees. Okay, so now let's solve for X. And we did one of these in our lesson today. We're going to subtract 90. So we have 2x left over here, and 360 minus 90 is 270. All right, now can I divide both sides by 2? I sure can. So what is left? X is going to be equal to 270 divided by 2 is 135. Now we're talking about degrees, so this tells me that an octagon has 131 angle of an octagon is 135 degrees. So this angle right there and all the others is 135 degrees. Can I check that? Can I verify that? Sure, I could. I could say, well, if that's true, 135 degrees, now if that's true, 135 degrees, well, I can't check it right now. We'll get there another time. That's going to get to math 2. Don't do that. That's going to be high school. In high school, you'll talk about how you can see what the sum of the interior angles are going to be, and actually the sum of the exterior angles, but getting ahead of myself. That was just a couple days ago's lesson in a different class. Moving on, number 4. The height of the water in a tank decreases, so it goes down 3.5 centimeters each day. When the tank is full, the water is 10 meters deep. All right, so we have a nice big tank. When it's full, it's 10 meters high. We know the water is decreasing though at a rate of 3.5 centimeters each day. The water tank needs to be refilled when the water height drops below 4 meters. So it's kind of like a safety valve at 4 that says, okay, when you get to 4, it's time to like refill. So we know it can get up to 10, but 4 says refill. Notice these are meters here, and it's decreasing in centimeters. Okay. The water, okay, so write a question that could be answered by solving the equation 10 minus 0.035 d equals 4. Now you might think yourself, why is this such a small number here? Well, that's because we're talking about meters here, and the decrease is in centimeters. So we make it in centimeters compared to meters. That's why it's just a small number. So this is the height of the tank when filled is decreasing at that rate. How many days does it take at that decrease until it reaches the 4-meter refill mark? So you might say I have a question like, how many days will it take before the water level in the tank needs to be refilled? So in this problem here, you're solving for D, which looks like days. So write yourself a little story about how many days will it take before the water decreases to the point where it needs to be refilled at 4 meters. Now you'll want to use the words to make sure you have the right words and the numbers in your story to make it work out okay. All right, B. Is 100 a solution of 10 minus 0.035 D greater than 4? Write an equation, write a question solving that solving this problem could answer. Okay, so 100, if it's a solution, you're solving for what? D's. You're talking about the number of days. So the question here is there enough water in the tank after 100 days? Okay, because you want to make sure that this is what? Greater than 4. So greater than 4 means there's enough water. It's greater than 4. Enough water is greater than 4 meters. If it's 6, you're fine. 8, you're fine. After 100 days is the question. After it goes for 108 days, is there more than 4 meters of water in the tank? So you write your own question to make that work out okay for you. All right, number 5. Use the distributive property to write an expression that is equivalent to each expression. So distribute. -3 times 2x is -6x. -3 times a -4 is a +12. 0.1 times -90 is actually going to be -9. And 0.1 times 50a is going to be a +5a. -7 times -x is a +7x. -7 times -9 is a +63. And 4/5 10y, okay, 10 divided by 5 is 2, 2 times 4 is 8, becomes, 10 divided by 5 is 2, right? So then you have 2 times 4, which is going to be 8. So we have 8y. And then over here, we have x, -x times 4/5, so it becomes a -4/5 x. And over here, we have 15 divided by 5 is 3. 3 times 4 is 12, and it's still negative, so -12. And that's our answer for that one right there. One more problem on the back side. Lynn's puppy is gaining weight at a rate of 0.125 pounds per day. All right, describe the weight gain in days per pound. So we want to flip the order of things around. So right now, we know that the weight of the puppy equals 0.125 pounds per day. We want to put this in terms of the D being by itself. So I want to get the D by itself, okay? So we can put a 1 here, because that's a 1. Let's divide both sides by 0.125. Okay, 0.125. Well, 1 divided by 0.125 is equal to 8, and that is for days. So if we want to write the other way, what can we say? That the puppy gains 8 days. It takes 8 days per pound is what it takes the puppy to gain some weight. Okay, weight gain in days per pound, 8 days per pound is what it takes. There you go, and that's all we have. Hope that helps you out. We'll see you next time.